If you're a neural networks person, then probably one of the biggest questions on your mind is, what's the next big thing, the next huge evolutionary step in neural networks? To do that, we need to take 3 different approaches that will help us triangulate in on where there's a likely direction for neural networks, the next generation, the hugely next generation to emerge. And those 3 steps are...
But before we get into that, this video is a re-edit of a previous version. We want a little bit tighter focus on 3 important things. The first of them is building a framework for a new neural networks class. Secondly, we need context, and we're going to provide it by looking at 2 very well-known neural networks classes. And finally, we're going to extract the key insights that have made these so powerful and so effective, and see if we can isolate important principles that will carry over into new inventions. So let's return to those 3 different processes by which we'll triangulate in on this new neural networks class.
Phylogenetic etymology, that is, we've been looking down the family tree of neural networks as they've evolved over the past, actually 50 years.
The next big step that we'll take in figuring out where we'll get the best direction in creating the next generation of neural networks is to look at the problem statements of some of the best work that's been done so far. We should take a look at the 2003 paper by Bly, Ying, and Jordan, the 2002 Contrast of Divergence paper by Hinton. We should also take a look at Steve Grossberg's 2021 book, Conscious Mind, Resonant Brain, in order to get a sense of how he's approached problems over the past 50 years. Those are just 3 examples of the kinds of problem statements that we want to look at. There will be more.
We're going to go back to a logical topology of neural networks invented, about 30 plus years ago, and see where that gives us an opportunity to see a different kind of map where there might be some room in the terrain for something new. Welcome in. I'm Dr. Aliana J. Morin, here speaking with you from Themsys Incorporated. We offer videos, blog posts, soon to be educational resources in artificial intelligence, neural networks, and deep learning.
So let's go back to the start of our story. Years ago, when dinosaurs ruled the earth and neural networks had just begun, there was such a thing as a logical topology of neural networks.
At that time, we're talking late 1980s, early 1990s, neural networks coming out of various different corners. People were piling into the discipline. It was exciting. It was the next new thing, but it was very disparate. Researchers had worked typically in isolation for years. They'd published in oddball journals. So papers were showing up, new architectures were showing up, and people were looking at them and saying, whoa, I didn't know that this one existed, and wow, there's that one too. So we had to put together some sort of structure, and I did that. It was a part of my first book on neural networks, and here's where it led us. We had a structure come out of this effort that was 6 different classes of neural networks.
We're going to take a look at each of these classes with a point of view of identifying what it was, what made that network work, because we want to pull out the features that we think are really important that carry over from class to class so that we have a handle on the best things that will help us create the next generation of neural networks.
What we're going to establish today is that the notion of different classes, major archetypal groupings or architectures of neural networks, was a first pass. What we need to do is revise that, and as we do that revision, it's another method, it's another vector that will let us see the big picture, the whole. So join me. We're going to have a very quick look today.
Let's get started. Let's do a quick sum up of this first class. First, to state the obvious, it's composed of neurons. The neurons have connections, and the neurons themselves have activations. I'll also call these nodes. So we've got a system of interconnected nodes, each of which are connected to each other in a specific pattern, input, hidden, output. And in a simple multilayer perceptron, the nodes can have varying degrees of on and offness. We'll see some networks, like the next class, where the nodes are bi-state, either on or off. This kind of neural network, as with most, are a form of sausage-making machines, meaning you put stuff in at one end, the input data, and you turn the crank a few times, and out plops a something, a classification, an autoencoder fill-in, something that is a result of a process being done to the input. You stop doing inputs, you don't have any more outputs. Finally, we'll note that the system is trained doing something that has to reach a minimum. In this case, we're reaching a minimum across the summed squared error. There are other forms of stochastic gradient descent, but they're still in the same category. Let's sum up what we have so far. We have neural networks consisting of nodes, each with interneuron connections and activations. These neural networks are sausage machines. They're input, output, and if you stop giving them input, they don't give you any output. If you want to have temporal memory, it requires a lot of fussing, something like a long short-term memory. Or, of course, transformers. Finally, something always gets minimized. In the case of this straightforward multilayer perceptron type of architecture, stochastic gradient descent, for example, backpropagation. We have a pretty good handle now on that first class of neural networks, the multilayer perceptrons, so let's move on to the second class, Class B, laterally connected neural networks, initially single layer. This is a class originally exemplified by the Hopfield neural network. It was actually the little Hopfield neural network. It had a set of nodes, each of which were connected to each other. Let's redraw our picture from the original electrical engineering style diagram to one that's more classical neural networks. We'll still see the same connections between every node. The Hopfield neural network was designed to be a content-addressable memory device. It had relatively poor performance, which led to the Boltzmann machine later, but the important point now is not just that we have the lateral connectivity throughout, it's that the neural network achieved its connection weights through minimizing a free energy equation, the Ising equation. This is a big distinction between the Boltzmann machine and Hopfield neural network class and the Class A neural networks of multilayered perceptron types that achieve their connection weights through minimizing a summed squared error across the output nodes. When we try comparing a Boltzmann machine to a multilayer perceptron architecture, we see that the original Boltzmann machine simply has a lot more connections. Every node connects to every other one. The task of creating a Boltzmann machine kind of neural network that was isomorphic with a multilayer perceptron was achieved with the restricted Boltzmann machine, and in the restricted Boltzmann machine, the visible nodes, both the input and the output, if we choose to make that distinction, connect only to the hidden nodes and vice versa. This allows the connection to be isomorphic with a multilayer perceptron. Let's do a quick recap about what we know about the restricted Boltzmann machine, and to make it easy, let's start calling that an RBM. The defining characteristic, as with the regular Boltzmann machine and with the Hopfield, is still the statistical mechanics Ising equation, and this equation is minimized to achieve the connection weights between the nodes. Now that we've spent some time with this, we realize it's less about the architecture, in other words, the numbers of layers, and more about the energy equation. The RBM is foundational for deep learning and for generative adversarial networks, or GANs. Let's summarize what we know about RBMs. First, in their heart of hearts, in their truest nature, they are essentially autoencoders. We can make them do a classification task, and when we do that, we need to put the nodes that act as the classifier outputs in the set of visible neurons. That is, we need to encode the patterns that we desire. The resulting hidden node activations, those are the features, can be used as inputs to a next processing layer. This is what makes it possible to have the deep architectures. Now we realize that we've covered a lot, and you might like some backup. The best source for this particular aspect of the discussion, the restricted Boltzmann machines, or RBMs, contrasted and compared with the multilayer perceptrons, or MLPs, is found in a blog post from Themysys produced on February 4th, 2022. More recently, the blog post that goes with this particular whole YouTube was produced May 16th, 2023. If you happen to lose track of these dates, it's still easy to find. Just do a little search on Themysys, logical topology, and maybe the category term, the future of AI. So let's wrap this up. This covers the first two neural networks classes or categories. The first class is the MLPs, or Multilayer Perceptrons, trained with some form of gradient descent, and the second class was originally laterally connected, but now we're re-envisioning it as the class of neural networks governed by minimizing an Ising free energy equation. That would include the Hopfield Boltzmann machine and Restricted Boltzmann machine. Now, obviously, we still have a lot of neural network material left to cover, but let's close for now. The easiest way to make sure that you learn about the next Themyscus YouTube or the next Themyscus blog post is to go to the Themyscus website, go to the About page, scroll down, find the opt-in form, and opt in. Every time we publish something new, we send out an email, and that way you'll be fully informed. And of course, we always invite you to do the like, subscribe, and hit the notify bell with our Themyscus YouTubes. Thanks for joining us once again. Aliana Maren from Themyscus Incorporated. We'll look forward to seeing you soon. Have a great day.